This video is going to be about spectroscopy and Beer's law. Spectroscopy is a very common analytical technique for determining concentrations of analytes in various matrices. Most common would be in the gas phase or in a liquid phase. So using spectroscopy back in the late 80s and early 90s, we were able to determine how the ozone layer was changing as a function of latitude. So if you know, back then there was a big deal about the ozone layer and how it was depleted and thinning over the South Pole. So this graph shows the concentration of ozone decreasing as it gets closer to the poles, so at higher latitudes down here. Now each molecule, whether it's ozone or oxygen or copper or anything else, has a specific wavelength that it absorbs light at, or a range of wavelengths. So ozone has an absorbance maximum of somewhere around 230 nanometers. So if we shine light at that specific wavelength at ozone, a lot of that light is going to get absorbed, and we can use that information to determine how much ozone is in a particular sample. And we'll talk more about that later on in this section. So when we talk about spectroscopy, we have to talk about electromagnetic radiation or light, because that's what we're going to be using to measure different concentrations of our analyte. Now it could be visible light, it could be infrared light, it could be X-rays. Many different types of electromagnetic radiation can be used in spectroscopy. What we use in lab is visible light, but it can be different types of electromagnetic radiation. So as you probably learned in physics already, light can be described as both a wave and as a particle. As a wave, electromagnetic radiation consists of perpendicular waves, as shown in this figure down here. And the distance between those waves is called wavelength. It's measured in nanometers. And the frequency is the number of oscillations or waves per second measured in hertz. And the speed of light is related to both the wavelength and the frequency of light by this equation here. And the speed of light being 300,000. And the speed of light is approximately 3 times 10 to the 8 meters per second. Or to put that into context, it would make its way around the Earth about 7.5 times every second. So here's a quick example. What is the wavelength of radiation in your microwave? So most microwaves have a frequency of 2.45 gigahertz. So what is the actual wavelength of microwaves in your microwave used to heat up your food? Well, from the previous slide, we know that the speed of light equals the wavelength times this frequency. We're trying to figure out what the frequency is. We know that the speed of light is 2.998 times 10 to the 8 meters per second. That's going to be equal to wavelength times 2.45 gigahertz. Now, that's gigahertz, so that's 10 to the 9. So we have to go 2.45 times 10 to the 9 hertz to make sure everything is in the right units. Okay, if we solve for wavelength, it ends up being 12.2 centimeters. So the wavelength of light in your microwave is 12.2 centimeters. So one easy way to prove this to yourself is to take maybe 9 slices of bread, butter them on the entire surface, and if your microwave has one of those turntables, you're going to want to remove that. Place the buttered bread in the microwave and set it to go. And what you will notice is that the butter will melt in certain places on the bread, and the distance between the spots that are melted is going to be the wavelength of the microwave. So that's going to be approximately 12 centimeters. Now, of course, light can also be thought of as a particle or a photon, and each photon has a specific energy associated with it. And that energy is going to be related to Planck's constant and the frequency of light. And since we know the frequency of light is related to the speed of light and its wavelength, the energy is also going to be related to the wavelength of light. In fact, it's inversely proportional to the wavelength. So long wavelengths of light, such as infrared or microwaves, have low energy, whereas short wavelengths of light, such as gamma rays or X-rays, are going to have high energies. So on the graph to the right, these guys up here are going to have the higher energy, and these guys down here, comparatively, are going to have lower energy. Now, H in this equation is Planck's constant, 6.6 times 10 to the minus 34 joules per second. And we'll use that in the next example to determine how much energy a photon would give to a molecule. So here's the question. By how many joules is the energy of a molecule increased when it absorbs visible light with a wavelength of 500 nanometers? So if our wavelength equals 500 nanometers, we have to put that into meters. So that's going to be 500 times 10 to the minus 9 meters. And from the previous slide, we know energy is equal to Planck's constant times the speed of light over the wavelength. We're trying to solve for the energy. So we know Planck's constant, 6.626 times 10 to the minus 34 joules per second. The speed of light is 2.998 times 10 to the 8 meters per second. And the wavelength, 500 times 10 to the minus 9 meters. So if we solve that, we get an energy of 3.96 times 10 to the minus 19 joules. So a very small amount of energy, and that makes sense. One molecule, a photon of light, giving it a little tiny bit of energy. So what happens when we shine light at different wavelengths at molecules? It's going to depend on the energy of that light. So it can do a number of different things. So if we have low energy light, so these guys down here, all that can really do is rotate a molecule or cause the molecule to vibrate. So it's not doing anything terribly destructive, but it is causing it to move a little bit. So rotational motion takes less energy because lower energy photons are able to cause a molecule to rotate. And notice that this is in the microwave region. So microwaves, the main purpose is to cause the moisture or the water in your food to rotate and essentially heat up. A little bit more energy causes the molecules to vibrate. And now if we look at higher energy light, so starting from the visible light and going up to X-rays and even beyond X-rays, can cause what are referred to as electronic excitation. So electrons are going to be promoted from a ground state to an excited state. And if we continue on to higher energy light, X-rays, that can do things like break chemical bonds. So again, low energy light, long wavelengths, and high energy light has short wavelengths. So I just want to take a closer look at what happens when photons are absorbed by a specific molecule. So molecules can absorb light, and it's going to have to be at a specific wavelength. So remember when we talked about ozone, it had a maximum absorbance of somewhere around 230 nanometers. If we go far below 230 or far above 230 nanometers, then ozone is not going to absorb that light. It'll just go right through the molecule. But when it does absorb light at the wavelength that is specific for that molecule, what happens is an electron that is in the ground state will be promoted to one of several excited states. So it could stop there, it could go a little higher, depending on how much energy that photon is given that particular molecule. So that's called absorption. So when a photon is absorbed, that energy is now in the molecule itself. So that photon does not make it through the sample, it gets absorbed into the molecule. That energy is taken by the electron to allow it to go into a higher energy state. So after an electron is absorbed, what happens is that the electron returns back to the ground state in a process called emission. So in that case, what happens is the energy from the electron is now re-released as a photon. And then that photon can be measured by a device which can allow us to determine how much of a specific molecule is there. So we can either measure absorbance, so how much light disappears, right? So we shine light at a blank sample that all the light would go through, so we wouldn't have any absorbance. We add some analyte to that mixture, and then some of that light is blocked, so we get a reading that would give us an absorbance. And the more of our analyte is in there, the more of that light will be absorbed, and that will give us an indication of how much analyte is in our sample. Or we can measure the emission of our sample. So as the electron is going back down to the ground state, releasing a photon, if there's more of the analyte in the sample, more photons are going to be released, which will give us a bigger signal. And again, that will be proportional to how much of our analyte we have. So when we talk about shining light at a sample, we can talk about it in terms of transmittance or absorbance. I've been talking about absorbance, but we'll talk a little bit about transmittance. So transmittance is how much light passes through the sample. So we have our equation at the top here. So transmittance being T is going to be the ratio of the light that passes through the sample divided by the light that strikes the sample. So the light that doesn't get through. So transmittance, the fraction of light that passes through a sample. And if all the light passes through the sample, transmittance equals 1, or T equals 1. If no light passes through the sample, T equals 0. Now, most of the time, we'll talk about percent transmittance rather than transmittance. So essentially, we just take the number that we get for transmittance, for example, 1, multiply it by 100. So when all the light passes through the sample, the transmittance would be 1, or the percent transmittance would be 100%. So percent transmittance ranges from 0 to 100%. Transmittance ranges from 0 to 1. Now, the problem with transmittance is it's not linear with respect to analyte concentration. And as we've seen with our calibration chapter, we like to work with straight lines. Things that are linear are a lot easier to deal with because we can predict how the signal is going to change as a concentration changes. So if our signal is not linear with concentration, it's a little bit harder to predict how things are going to work. So what we can use instead of transmittance is absorbance. And absorbance is the amount of light that is absorbed by the sample. And it's given by this equation here. So you can see it's related to transmittance. It's actually the negative log of the transmittance. So absorbance is a logarithmic scale, but it's linearly related to concentration. So there we have our nice linear relationship, and we can more easily use absorbance to determine concentrations. So when no light is absorbed, percent T equals 100, so 100% goes through, absorbance is going to be 0 because none of that light got absorbed. It all got through the sample. When 90% of the light is absorbed, our percent T equals 10. 10% got through, 90% was absorbed, and if 90% is absorbed, our absorbance ends up being 1. So let's just do a quick example to see how absorbance and transmittance are related. So what absorbance corresponds to 99% transmittance and 0.1% transmittance? So we want to calculate absorbance. We know we'll be using absorbance equals negative log of T, but also note in this question that we're given percent transmittances, but the equation requires transmittance. So for the first one, absorbance is going to equal the negative log of 0.99, which equals 0.00436. Okay, so 99% of the light got through. Not a very large absorbance, makes sense. For the second one, absorbance is going to equal the negative log of 0.001, so 0.1%. And if we do that calculation, our absorbance ends up being 3. So if only 0.1% gets through, that means most of the light is absorbed, so we would expect a relatively high number for absorbance. Now, I will say most of the time when you're working with absorbance, you want to make sure your sample absorbs between 0 and 1. Because it's a logarithmic scale, you'll get a better signal differentiation between absorbance of 0 and 1. So from the previous slide, remember that 90% transmittance was an absorbance of 1. So if I were to draw all of our absorbances and transmittances on a simple straight line, so here we have absorbance and transmittance. So if we have 100% transmittance, our absorbance is 0. And if we have 10% transmittance, absorbance is 1. So notice how much of the scale we have when we're working between absorbances of 0 and 1. We have 90% of that scale to work with. Now, if we take this a little bit further, if we have 1% transmittance, so somewhere down here, that's 1% transmittance, our absorbance there is going to be 2. Notice we don't have much range here. So for signals giving us an absorbance between 0 and 1, we have 90% of that scale to work with. For signals that give us an absorbance between 1 and 2, we have 9% of that scale to work with. And if we go even farther, a percent transmittance of 0.1%, so what we just did, we have an absorbance of 3. Now we have an even smaller range to work with. So most of the signal differentiation can be measured between an absorbance of 0 and 1. So it's always best to make sure all your samples and all your standards have absorbances of less than 1. If they don't, you're going to have to dilute your samples to make sure they do. And that's just going to give you the best signals for your particular sample and allow you to get the most accurate results. Okay, so let's do another example. The absorbance of a sample was determined to be 0.568. What would the corresponding percent transmittance be? So to do this, we're going to have to solve this equation for T, and it kind of looks like the pH equation, right? pH equals the negative log of the concentration of H+, absorbance equals the negative log of transmittance. So it's the same rearrangement, so it ends up that T equals 10 to the minus A, the minus absorbance. So T equals going to be 10 to the minus 0.568, and then T is going to equal 0.270. And if you want to convert that to percent T, just multiply by 100 and you get 27%. Okay, so now let's talk about Beer's law and how we can use spectroscopy to measure concentrations of analytes. So Beer's law relates the absorbance of a sample, A, to the concentration of the analyte, C. So A is absorbance. Absorbance doesn't have any units. C is concentration, units of molarity. And we have epsilon, which is called the molar absorptivity. So that's just a number that corresponds to how much light a particular analyte absorbs at a specific wavelength. So this number is going to be different for different compounds at different wavelengths, and it's just basically a constant. And B is the path length. So that's how far the light has to travel through your sample. So if you've done one of the spectroscopy labs in lab, the iron vitamin lab or the copper EDTA lab, notice that you were using little cuvettes for your sample, and the width of that cuvette represents the length that the light has to travel through in order to get from one side of it to the other. So in most cases, it's going to be 1 centimeter. In lab, that's what it is, because each of those cuvettes is 1 centimeter square. But it can be any other value. It can be less than a centimeter, it could be bigger than a centimeter, and it depends on the dimensions of that particular cuvette. So the graph on the right just shows you how different concentrations of a specific analyte will show up on an absorbance spectrum. So an absorbance spectrum is a graph that relates absorbance on the y-axis to wavelength on the x-axis. So you can see here that this particular analyte doesn't really absorb anything on the extremes, so say between 400 and 475 and between 600 and 700, because we don't have much of a signal. You can look at the blue line to get the best example of what I'm talking about. So if we use a different wavelength, say one of these wavelengths up here, so that's somewhere around, say, 510 or 520, that particular wavelength is giving us the biggest signal because this particular analyte absorbs most light at that particular wavelength. So we're able to measure lower concentrations at that particular wavelength because that analyte absorbs that light at that particular wavelength. So with Beer's law, absorbance is proportional to concentration. So when you plot absorbance versus concentration, you should end up with a straight line. Molecules will absorb at different wavelengths, so different molecules will require different wavelengths for analysis. So in lab, you did one analysis using copper, and that required a wavelength of about 760 nanometers. And another example you did in lab was iron, in which you used an absorbance somewhere around 500 or so nanometers. So when doing an analysis, it's always best to choose the right wavelength, the wavelength that your particular analyte absorbs most strongly, because in that case, you'll get the best signal and you'll be able to measure smaller concentrations of your analyte. Okay, so let's do a question using Beer's law. So we have a solution where its preparation is described, so dissolving 25.8 milligrams of benzene in hexane and diluting it to 250 milliliters. It gives an absorbance peak at 256 nanometers and an absorbance of 0.266 in a 1 centimeter cell. If hexane doesn't absorb at 256, find the molar absorptivity of benzene. So this is actually an important statement here. If hexane doesn't absorb at 256 nanometers. If hexane did absorb at 256, then some of this signal here, the 0.266, would be from hexane. But you don't want it to be from hexane. That's the solvent. You want your signal to be only from benzene. Okay, so this question is telling you that benzene is the only thing that is giving you that signal. So we know that we're going to be using Beer's law. So we're going to be using A equals epsilon BC, and this question is actually asking us to find what epsilon is. So how do we do that using this equation? Well, first of all, we're given an absorbance, so we're fine there. We're given a path length, B, of 1 centimeter, so we're good. The only thing we're not given is a concentration, but we're given a mass and a molar mass, so we can determine what the concentration of benzene is in that particular sample. So we would have the concentration of benzene equals a 25.8 milligrams, so that's going to be 25.8 times 10 to the minus 3 grams, and multiply it by the molar mass. That's going to give us moles, and then if we divide that by the volume, that's going to give us a concentration, which ends up being 1.32 times 10 to the minus 3 molar. So now that we have concentration, we can rearrange Beer's law to solve for epsilon. So epsilon is going to equal absorbance over BC. And if we plug in the numbers, we're going to have 0.266 over 1 centimeter multiplied by 1.32 times 10 to minus 3 molar. And we end up with 201.3. And what are the units? So we have on the bottom of this fraction centimeters and molar. So we're going to have centimeters to the minus 1, molar to the minus 1. So there's our epsilon. Now the next part of this question says if the cell is 5 centimeters in length and the sample had an absorbance of 0.070, find the concentration of benzene. So luckily we already determined what epsilon is in the previous question, so we have epsilon. Now all we have to do is solve in this case for concentration. So concentration is going to equal the absorbance over path length times epsilon, and we know the absorbance is 0.070. The path length is 5 centimeters in this case, and the molar absorptivity 201.3 centimeters to the minus 1 molar to minus 1. And if we solve that, we end up with a concentration of 6.95 times 10 to the minus 5 molar. So what if we have a multi-component sample? So there are 2 different metals in solution, both with different colors and absorb at different wavelengths. If there are no interaction between the compounds of a mixture, then the absorbance at a particular wavelength is the sum of the absorbances from all species at that wavelength. So for example, if we have a cobalt and a chromium solution, and they each have their respective maximum wavelengths. Okay, so chromium might absorb at a specific wavelength, cobalt will absorb at a different wavelength, but some point in their absorbance spectrums, they might overlap in how much they actually absorb. So it might look something like this, where we have an absorbance spectrum of cobalt, which might look something like this. So its wavelength of maximum absorbance is right there. And then we have chromium, which might look something like this, where its maximum absorbance is here. So we have absorbance and wavelength. Okay, so that's our absorbance spectra for both cobalt and chromium. Okay, so here's cobalt and here's chromium. Now if we choose the maximum wavelength for chromium, as right here, you can see that there's a little bit of absorbance also from the cobalt. So when you measure the mixture at that particular wavelength, you're going to get a signal both from the chromium and from the cobalt. So you're going to have a sum of both of those signals. Okay, so absorbance is additive. And again, this is if there is no interaction between those compounds. So to determine what the concentrations of each of those components is, you would have to use an equation like this. We're essentially adding 2 different Beer's laws. So I mean, the Beer's law for component 1, the Beer's law for component 2, and solving a simultaneous equation. And from there we can determine what the concentration of cobalt and chromium. Now this particular lab we're not actually doing, so you don't have to worry too much about this, but just know that absorbances are additive. So I'm going to end off here with some limitations to Beer's law. So most of the time Beer's law gives you a straight line, but it can deviate from linearity if there are certain conditions. So we could have a positive deviation or we could have a negative deviation. And the three different types of deviations are fundamental, chemical, and instrumental. So let's talk about the fundamental deviations from linearity. So Beer's law is actually limited to low analyte concentrations. If the concentration of analyte gets too high, then the molecules no longer act independently from one another. And so they're not going to have the same type of linear relationship between absorbance and concentration. So the resulting interactions might change the absorptivity, and because of that, we're going to have a deviation from linearity. Usually this is a negative deviation. And absorptivity also depends on the refractive index. So at higher analyte concentrations, the refractive index of the sample is going to change. So that's going to change how the light passes through the sample. The refractive index basically is a measure of how the light bends as it enters a sample. So as the concentration of the analyte changes, light is going to bend a little bit differently, and if it bends a bit differently, it's not going to be getting to the detector the same way as it would have if it was essentially going straight through the sample. So if I were to exaggerate this here, if we have a cuvette and we have a low concentration sample, then the light is essentially going to go straight through. But if we have a high concentration of sample, the light might bend a bit as it goes through. So if the light is not going straight through, it might not reach the detector in the same way as it would if it was just going straight through the sample. So at low concentrations, the refractive index is largely unaffected, but at higher concentrations, that refractive index could change such that we get a negative deviation from linearity. Now, some chemical limitations to linearity, they occur when analyte molecules are involved in an equilibrium reaction. So if the analyte is actually reacting, doing something in the solution, then that can cause problems because the absorbance of the solution is going to be changing, for example, depending on the pH of the solution. So if you have an equilibrium reaction with acids and bases, and varying concentrations of the weak acid is going to change how the sample absorbs. Okay, so varying concentrations are going to result in differences in pH, and this is going to result in different amounts of that acid that has ionized. So if we have different amounts of acid ionized, we're going to have different amounts of analyte. So we're going to have to use something like a buffer to make sure that the pH remains constant. Otherwise, we're not going to get a good reading on our sample. And this can be either a positive or a negative deviation. Now, instrumental limitations of linearity occur because Beer's law assumes the analyte is absorbing a single wavelength of light. But that's not true, because if we look at absorbance spectra, the ones that I drew on a previous slide, the one for ozone, or the one right here, notice that it's absorbing over, a wide range of different wavelengths. So we're going from about 400 to 550 in this case. So we have to avoid this by making sure that we choose the wavelength of highest absorbance when we're doing our analysis. So this point right here. So if we're at the very peak, then there's not going to be much of a deviation from the signal if we're a little bit to the left or a little bit to the right of that particular point. Now, if we choose a wavelength somewhere down here on the slope of this curve, if the wavelength varies a little bit on either side of whatever this value is here, say 550, notice that the signal can change quite drastically, right? So that's not a very large change in the wavelength, but the signal is changing quite a bit. And again, this can be a positive or a negative deviation. So that's all I have for spectroscopy. And as usual, if you have any questions, feel free to ask.